Now I'm going to take a little bit of a quantitative look at collision theory with the Arrhenius equation. Collision theory tells us that the overall rate of reaction comes from how many successful collisions you have over time. The more successful collisions leads to a faster rate. And so we can break that down into kind of basically three ideas. The rate is going to be based off the total number of collisions. Molecules have to collide in order to react. So then the question is, what ratio of those collisions have the correct orientation? And then what ratio of those collisions have enough energy? So basically total collisions, and then we have these specifications of this idea of what makes a successful collision. It's going to be about that orientational dependence and the energy dependence. So this is our theoretical interpretation of what a rate is made up of, or why and how rates are determined. We can relate that to the experimental description that comes from the rate law. Rate is equal to K times the concentration of A raised to its order, concentration B, whatever the reactants are, raised to their order. And so this theoretical description needs to jive with that rate law, the experimental description. And so we can see that basically this concentration gives us the total number of collisions. That is why we use concentration. That's why we don't use total moles, because if you have a lot of moles, but they're really spread out, then you're not really seeing a lot of collisions. So you have a lot of reactants in a tight space, right? In a small volume, that would lead to high concentrations, lead to high numbers of collisions. So that's what that is. So that means this rate constant needs to have all the information about the idea of successful collisions. So large or high values of K correspond to a high ratio of successful collisions. So all of these ideas, all this concept from collision theory of what makes a reaction or a collision successful leading to a reaction, all is kind of going to be cooked in to that K value. So what I'm going to do is kind of unpack what does that K describe. So the Arrhenius equation gives us a representation of what K is quantitatively. We have K is equal to capital A, and then we have the exponential, that's an E raised to the power of negative EA, activation energy, divided by RT. Okay, so this capital A is a new thing. That is the frequency factor. The frequency factor is unique for each given reaction. So if you have a chemical reaction, you have a value for A. That's still just a constant. It's just going to be a number. So then EA, that's the activation energy. So that's the energy of that barrier. What is the energy required to break those bonds, to get to the transition state, get your change. R is the ideal gas constant. 8.314 joules per mole Kelvin is common. You'll note this is the same one we used for the Clausius-Clapeyron equation. It's the same idea, what we're working through. And then T is my temperature in Kelvin that I'm looking at. Beyond just the kind of variable names or the definitions, we're going to talk about what the kind of purpose or interpretation of this equation is. So K, rate constant, is describing the ratio of successful collisions. We can then parse out what it's equal to, being the two requirements for successful collisions. So this A constant, called our frequency factor, just describes orientation dependence. Okay, so this is the idea of, how hard is it for the molecules to collide in such a way as to have the right atoms connect with the right forming bonds. You want to get those atoms to collide the right way, this idea of sterics that we talked about. This is just a constant number, and so the Arrhenius equation still doesn't really explain this number. It's just, or this ratio. It just says there is a number A. Importantly, it doesn't depend on temperature. And one of the reasons why we just kind of punt on it is because it's really hard to control. You can't change your reaction conditions to affect orientational dependence. It's just there. But importantly, it doesn't depend on temperature. It's just a constant number. Some reactions, it's really hard. It's very rare to get the right orientational dependence. Some reactions are easier. The molecules are smaller. They're just kind of collide. It's a simpler change. But this is just another number. We're just not going to worry about that in the Arrhenius equation. We're just going to move it out and separate it from the temperature dependence. So this exponential term describes the energy dependence of collisions. the fact that collisions need to hit each other with, or molecules need to collide with enough energy in order to break those bonds to overcome the activation barrier. RT, that term multiplying R times T, gives information on the amount of energy and the amount of motion due to temperature among molecules, kind of an average energy of those molecules. And so what this is showing is basically how this overall term is giving the percentage or proportion of molecules that are going to be colliding with enough energy to break the bonds and overcome the activation barrier. What this overall tells us is that as temperature increases, this term will increase. So the capital A doesn't depend on temperature. So the temperature dependence, EA, is constant. That doesn't change with temperature. R doesn't change with temperature. So the only thing that changes is the actual T, the actual temperature. As that goes up, it's in a fraction, it's in the denominator, so that fraction gets smaller. It's negative, you're taking an exponential of a less negative number, so it does increase. So overall, it does increase. That's the important takeaway from this. The Arrhenius equation shows us why and how rates increase with temperature. As the temperature increases, K gets larger. You don't change anything with the orientational dependence. You don't change the activation barrier. You just make the molecules are moving faster, so they're colliding with more energy, and it is more likely that a collision will have enough energy to overcome the barrier and cross through the transition state into products. And so what this does is it lets us predict how much you can increase the rate with temperature. And that's the motivation for coming up with the Arrhenius equation. We can kind of experimentally learn that faster or higher temperature leads to faster rates. So this lets us predict exactly how much faster. And it's all in the rate constant, and it comes from that exponential term. One of the most useful or practical applications of the Arrhenius equation is that you can take the natural logarithm of both sides and it turns it into a linearized form of the equation. And so what we can kind of see is that the ln k is like the y, the ln of a is like your b, that's your intercept, EA divided by r is your m term, your slope, and then the x is 1 over the temperature. And so what we can do with that is basically the intercept, we can figure out a and then the slope would be negative EA over r. And so what you can do is you can create this plot by determining the rate constant K at multiple temperatures. You take the natural log of the rate constant K, you do the inverse of the temperature, you can plot them out, fit a line, and this is experimentally how most activation energies are obtained. It's harder to get A out of this, it's easier to get the slope. The A is a little more testy, but you can get slopes like this and you can figure out activation energies. And this is how we do experiments to determine A. You know, we've looked at previously ways to get rate constants. You can use the initial rate method, you can use your integrated rate laws, you can use half-life. So you do those experiments at multiple temperatures. That lets you determine what the rate constant is at those different temperatures, and then you can figure out the activation energy, which once you know the activation energy, you can then be able to control and predict how you can control the temperature at control the reaction rate at various temperatures using this Arrhenius equation. In terms of applying the Arrhenius equation, once you know the activation energy, it's more common to see the combined Arrhenius equation, which looks like this, which may have a slightly familiar form. And so what this lets us do is look at the temperature dependence of the rate constant. So we use the last form to analyze experimental data to determine activation energy. Once we know the activation energy here, what that lets us do is we can figure out how changing temperature affects rate constant, which means how changing temperature affects the rate of reaction. So if we want to make our reaction faster by changing the temperature, we use this equation to figure out how we need to change our temperature. Or, hey, this temperature is going to get hotter. How much faster is the reaction going to get? Or colder, is my reaction going to slow down? Those sorts of things we can start to figure out. You also notice this looks very similar to the Clausius-Clapeyron equation. That's not accidental. It is because the Clausius-Clapeyron equation is an activated process. You are trying to evaporate. Molecules are going from the liquid into the gas. That's an activated process. There's a barrier to it, similar to the activation barrier for any process. In the case of evaporation, that barrier is the enthalpy of vaporization, so that's why we get the same relationship. Let's apply the Arrhenius equation to make some quantitative predictions about how we can control reaction rate using temperature. If the activation energy of a process is 34.5 kilojoules per mole, at what temperature will the rate be 4 times that at 200 degrees Celsius? This is a very common application. We know where you can control rate using temperature. You're at 200 degrees Celsius. You want the reaction to go 4 times faster. What temperature do you need to raise it to? So one of the whole purposes of coming up with collision theory and the Arrhenius equation is to predict and control reaction rates. So we want to be able to use it to work through the idea of, at what temperature will the rate be 4 times that at 200 degrees Celsius? So I want this rate to be faster. I want to know what temperature I would need to go to in order to get that faster rate. And so if I want to make it go faster, and this is where the Arrhenius equation comes up. And so we got our equation here. ln K2 over K1 is equal to activation energy over the gas constant, 1 over temperature 1 minus 1 over temperature 2. And so we know what we want is a temperature. So what temperature will the rate be 4 times faster? So we want that. And so we're given T1, 200 degrees Celsius. R is a gas constant. EA, activation energy, is right there. And so these rate constants right there are the information we're not given. And in general, it's pretty common to not be given them or to even care what they are. Because rate constants are difficult to come from experiments. And you don't necessarily know what they would all be, but we can use this fact that it's 4 times faster. The temperature dependence of rate is all contained within the rate constant, right? If you think about the rate law, you have rate is equal to K times concentrations. Concentrations don't change with temperature. The order doesn't change with temperature. And so all of the dependence of the rate on temperature all is folded into these these rate constants. And so if the rate is 4 times faster, so if we have, that if rate 2 divided by rate 1 is equal to 4, that would imply that your reaction at rate 2 is 4 times greater than rate 1. You know that also means that K2 divided by K1 is also 4. So this whole thing is gonna be 4. That ratio is 4. You don't know what the values of K1 and K2 are, but it doesn't really matter. You know that K2 is gonna be 4 times greater than K1, because if K increases by a factor of 4, then you know that that is all due to basically it being the K greater than 4. And that is what makes the rate faster, is the change in the rate constant. So we can, with that in mind, we can take our equation, plug some things in. So I have ln 4 is going to be equal to EA is 34.5 kilojoules per mole. R as my gas constant, I'm using 8.314 joules per mole Kelvin, just like Clausius-Clapeyron this equation looks like. We always use 8.314 joules per mole Kelvin, 1 over T1, 200 degrees C, minus 1 over T2. So we want to clean up some things with our units. Those need to line up. Joules and kilojoules need to be the same. And that should not be degrees Celsius. That should be Kelvin. So in this case, the kilojoules, I would need to multiply by 1,000, because that's joules per 1 kilojoule. And here I want to add 273. Because that is my conversion from degrees Celsius into Kelvin. generally, whenever we are working with temperature in an equation, we always need Kelvin. Delta T, we don't need. Delta T, we can get away with just using degrees Celsius. But if it's raw temperature in the equation, we always want it to be Kelvin. So 34,500 joules per mole, 8.314 joules per mole Kelvin. Those joules per mole are all going to cancel out. 1 divided by 473 Kelvin minus 1 over T2. We can work that out a little bit. ln of 4 is going to be equal to, if we do this division, I get 4,150 Kelvin. You can see that what happens unit-wise, the joules per mole cancel out, and it's 1 over Kelvin in the bottom of it, so that swaps up. 1 over 473 Kelvin minus 1 over T2. ln 4 divided by 4150 Kelvin is equal to 1 over 473 Kelvin minus 1 over T2. And then what I want to do is basically swap it. So the T2 needs to move over here, subtract out that, write that out. And that is something I can evaluate. Right? Those are all numbers over here now. Zero, 0.0178 inverse Kelvin, right? The Kelvin were on the denominator of that fraction on both sides. So I'd get T2 is equal to 1 divided by that thing. Which is going to be equal to 562 Kelvin. Which is great. That is a temperature. And the question now, what temperature? But because it was 4 times the rate at 200 degrees Celsius, the temperature that we're giving, or that we're going to give in our answer, we should probably keep it in Celsius. So that way it's an apples to apples comparison. So 562K minus 273 gives me 289 degrees Celsius. And so we can use the Arrhenius equation to guide our roll. So if we want to, increase the temperature by a certain factor, or if we have a target, or increase the rate by a certain factor, we can then guide how we set our temperature. One of the things you'll note is that we started at 200 degrees Celsius, which better comparison would be 473 Kelvin. We don't have to increase the temperature by a huge margin. It's not that we have to multiply the temperature by 4 in order to get the rate to increase by 4. It's because there's this exponential factor. When you increase the temperature, you can get really big effects, really big growth in the rate of energy. So you only have to increase the temperature by 89 degrees Celsius, and you get a factor of 4. It is relatively easier to do that. It does vary based on the rate or the activation energy that you see and the particular temperatures that you're at. In terms of getting that change, when you're at higher temperatures, it becomes more difficult to increase the rate by a bigger factor because your rate just is bigger at that time. And if you have a big activation energy, it's also difficult. But you can see these sorts of changes that we can see. But this is the kind of predictive chemistry we want to be able to do. How do I make the rate faster? We know that increasing the temperature will always work, but how fast do we need this rate to go? We don't need to blast the temperature up to like 800 degrees Celsius. We can just go to say 289, which is still hot, but it's a reasonable, and we can be efficient in how we increase our temperature in order to get a desired rate. So now that we've worked with the Arrhenius equation, we have our nice kind of description of collision theory. And that all goes hand in hand with the rate laws and integrated rate laws we had talked about previously. Those are all descriptions of experiment and predictions of what your experimental results will be. What is the rate right now? How can I make the rate faster by changing concentration? How will concentration change over time? Those sorts of things are really useful for predicting I have an experiment and what are the outcomes of that experiment going to be. Collision theory lets us explain a little bit of how reactions actually occur. We have these collisions between molecules, so we can start to predict ways, not just how the reaction rate will change, but what are ways that I can do? How can I design a reaction to make my rate change in a desired way? Why does concentration matter, right? That comes from collisions. How can I maybe chop up my bits of solid to increase a rate of reaction? Or potentially more importantly, how can I slow a reaction down, right? We don't make our fireplace grates out of iron powder. We make it out of giant chunks of iron, right? Using those sorts of ideas. Now with our temperature, we know temperature is one of the easiest things to control. That's why we store food in a cold refrigerator. That's why we use heat. Generally, we heat things up when we want the reaction to happen or happen more quickly. And so we can make those interpretations about make those predictions more quantitative with the Arrhenius equation. Exactly how much should I heat my reaction up in order to get a desired rate? So we kind of put all of these together to have a more comprehensive understanding of not only being able to predict what the rate is or understand what the rate is, but make predictions moving forward about how I can control the rate. And we'll want to continue to kind of gain some more insight into how these reactions work, understand the nuts and bolts of what really goes on in a reaction. All right, that is it. 3 questions on participation 2-3. You want to find all 3 of them, get them answered, and get those answers submitted over on Blackboard by Tuesday evening. The midweek 4 homework will be due Wednesday evening. Crystal Violet Kinetics Lab is going to be due Wednesday. We'll start to do that at Wednesday at 11 a.m. So you want to take care of those pre-lab questions, technique comprehension, and get the notebook set up. If you have any questions about anything, don't hesitate to reach out. There will be the answers to the participation that go live Tuesday night. Otherwise, I'll see you either on campus Wednesday or the second set of videos. And don't forget, next week we have the exam. If you have any questions about that, let me know. Wednesday on campus, perfect time to chat about it. Otherwise, enjoy the rest of your day. I'll see you around. Bye-bye.